Hello everyone and welcome to CS61B Discussion 2 Walkthrough. Today we're going to be going over scope, pass by value, and static versus dynamic types. Let's get into some announcements real quick. First thing, live lectures are now Q&A sessions and they will be like this for the rest of the semester. Please watch the lecture before you come so that you can ask Professor Hug any questions that you have. Next, there's a weekly survey due every Sunday. Please fill it out. It helps us on course staff know if what we're doing is working for you guys. Next, discussion and lab attendance is completely optional from now on, other than a couple mandatory labs. This means that instead of going to live discussion, you can watch this walkthrough instead. However, you will not get pacing points for doing so. In the same vein, lab partnerships are now completely optional, but you will need a partner for Project 3, so we highly recommend that you find someone that you can practice working with already. Exam prep sections will start next week, and that will include exam prep walkthroughs being posted starting next week. You should notify us on the Google form if you're interested in attending one of those. Office hours have started this week on Discord. Read up on what that means before you show up, because it's a little more complicated than our old setup. And lastly, if you need DSP accommodations for exams, please fill out the form on Ed as soon as possible. The more time you give us, the easier it is for us to accommodate you. Fabulous. Okay, let's get into some content review. The first thing we're going to talk about is primitive versus reference types in Java. So, the way Java works is when you create a new variable, it has this area in memory that just holds all of the variables. If I say int x, then it creates a new box here in our variable area. And it makes the box big enough to hold an int. So if I want to put int x equals 10, we can just plop a 10 straight into that box. Very straightforward. There's only 8 types of primitive types, and these are all of them. Now, reference types, you can think of them as being bigger items, like full objects, strings, arrays. Each reference type may even contain several other primitive types. And so, instead of wasting our variable space by allocating space here, say I wanted to create a dog object, I could create the variable in the same place and have a box. But instead of putting the dog object in this box, which is not really big enough, what we do is here we put a memory location. So that might look like some weird number that's a memory address for some other place in your system's memory. And then we visualize that by drawing a pointer to the object. So this is our dog object. And that's in a different place in memory, and all D has is an address so that your computer can follow that address and find the dog object. Now, where does this cause any issues? Where does this actually matter? Well, there's a couple places, and the most straightforward one is when we're trying to compare objects. So if I want to compare 2 integers or 2 doubles or 2 characters, it's straightforward. You've done this, I'm sure, in Python or in any other programming language. And all you do is x equals y. Equals equals, it checks what's in the box for x, so let's say that's like a 5, it checks this. For y, it also checks, the items are different, so it'll return false. Now, let's say you have 2 int list objects, right? So let's say you have, or 2 array objects, which is even more straightforward. So let's say you have A, which points towards the array 1, 2, 3. And you have B, which also points towards a different array that contains the same items. So in this case, if we do A equals B, what we're comparing is, again, the value in this box. And even though they're pointing at identical objects, because those two objects are different from each other, in that, for instance, if I did A2 equals 10 suddenly, and this became 10, B would not be affected because they're completely two different objects. Despite the fact that they're equal, this is going to return false, because it's comparing the memory address of the objects. So if we want to actually compare arrays, if we want to be like, okay, if arrays have the same items in them, then obviously we can just consider them the same array. So we use something called A dot equals B instead. And this will return true in this case. Don't worry too much yet about how dot equals works. We will cover this later in the semester. But this is a simple example of where reference types act differently than primitive types. Okay. Now let's talk about pass by value. So when you, this is just another example basically of how reference types and primitive types act differently. So let's just follow through this block of code and see what happens. So the first thing we do is we create an integer x, we pop a 5 into that box. Straightforward, great. Okay. The next thing we do is we create an array, an integer array. And remember when we talked about the last slide, the arrays are objects, so we have a pointer to where the array is actually stored. And our array looks like this. Now comes the interesting part. We're going to pass both x and array into a function called doSomething. If you've done environment diagrams in previous classes like CS88 or CS61A, I'm sure you'll be able to reference back to that for what I'm about to do. So now when we go into a new function, what we do is we create a new frame. And I'm not going to re-explain exactly what a frame is, but the short of that is we can't access x from inside doSomething. If I did x equals 5, your computer would error because it's like, I don't have any x in this area. So we don't have access to these variables while we're inside doSomething. So instead, let's figure out what we do have access to. We have two variables, y and a, which are passed in. So the first thing is the primitive type. We're passing in x. And what your computer does when you pass something in, is it takes the value stored at that variable and copies it into the new variable. So like that. So all we're doing is we're copying the 5 over from x over into y. Great, I'm sure that's what you thought was going to happen. The more complicated thing is, what about when we pass in r? So when we pass in r, the same thing actually happens. The same thing actually happens. We're copying in that value, which happens to be some memory address, over into a. So we're going to copy in this memory address, which means that a now also points towards the same address that r pointed towards. This allows us to actually edit r while we're in doSomething and have those changes be sustained even after doSomething is over. So if we run this first line, we set y equal to 16, and that's great, but this has no impact on x. X is not going to change because we change y. We have no way of changing x from inside this function. But because a and r both point at the same array, when we set a2 equals 4, your computer says, okay, let's go to a. Now what does a point at? A points at this array over here. Now let's find the second item, 0, 1, 2, and we set that to 4. And now doSomething ends, doSomething is over, we exit back out, and if we were to call r2 later in our program, this would return 4 instead. Okay. Let's talk about some very basic data structures. This class is going to get into some more complicated ones, but for now we're going to talk about arrays. Arrays, in essence, are just lists of items that can be indexed into using bracket notation. So you can think of an array as being, let's say, 1, 2, 3, 4, and you can access the whatever element by just having its index in this bracket. So if I want this 2, then I would do R1, and that would give me the 2. They are 0 indexed, which means that the first element is actually the 0th element. And so we have 0, 1, 2, 3. If we tried to call R4, this would error. So now we know how to use arrays. How do we create arrays? Well, there's two main ways you can create an array, and they should remind you of how we created objects in the last discussion. So the first thing we do is we declare that this variable will be an integer array. And of course, this is the name of our variable. And then on this side, we use our fancy keyword, the new keyword, which tells us we're creating a new array. And then we do something interesting here. So we say, okay, it's an integer array, very similar to our declaration, but then we put a number here. And what that number represents is the length of the array. The way Java arrays work is in the actual computer, so you have your pointer to some memory location. And that memory location is basically partitioned into a bunch of individual boxes that are the right size for whatever item you're putting in. So you're putting in integers, each block in your memory is exactly the right size for one integer. Since we partition out these blocks before we actually do anything, we can't change the size of the array once it's made. So this has some pros. First of all, it makes it very, very fast to find some item in the array. If I want like the third item in this array, which would be this item, all I have to do is, okay, what's the memory location? And then I add 3 int size. Don't worry too much, this is just more 61C stuff, but it's interesting and it lets you know why it's so stringent. And then suddenly you're right there already and you didn't have to do any fancy chaining or anything. It's very, very, very fast. The other way to do it is very similar. It follows the same basic structure, except instead of having a size here, you pre-fill it with numbers. And because you know how long that list you're providing it is, you don't have to tell it, oh, it's also size 3, because that's redundant information. You might be wondering, why would you ever use an array? They seem so strict, they seem so forced. Well, the first thing is, like I said, arrays are very, very, very quick. We'll talk about linked lists in a minute, but the thing that's great about arrays is that accessing any element takes an equal amount of time, which is not true for most data structures. The second thing is, because it's so strict, it's a lot easier for your program to catch possible errors before you're already running your code. Imagine your code takes a very, very long time to run, like a day to run, and there's an array problem all the way at the end of it. Because arrays are so strict, let's say you were trying to do, I want x.x4, which obviously doesn't exist because it's only length 3. In Python, this would run and then you would error at that point. But in Java, because everything is so strict, because the sizes cannot be changed, your computer has the ability to look over your code before it runs and prevent this from happening. Obviously, this won't stop all errors, but it does help alleviate a lot of them. Okay, we've talked about arrays. Let's talk about linked lists. So I'm sure you've seen linked lists before in previous classes, but we're going to go a little more in depth in this class. But for today, all we're doing is an overview of the syntax and what it means. So linked lists, in essence, are similar in purpose to arrays, but they have different pros and cons. So linked lists are modular lists that are made up of nodes that each contain a value and a pointer to the next node. So an example of a linked list, if I do int list equals, and then the box and pointer diagram for this would be like 2, 3. Let's say that's the end of our thing. So each node contains some value, which we call first in this class, and then some pointer to the next node, which we will call rest. The last block doesn't contain any pointer, it just contains null where the pointer should be. Instead of using the bracket notation that we saw with arrays, we'll use a more traditional dot notation, which is common for most classes, and we'll use intlist.get too. If you want to create an int list, again, it's very similar to how you created objects previously, and so int list here is just declaring what type. This one is its name, our fancy new keyword, and then calling the int list constructor. Now let's talk about linked lists versus arrays. So unlike arrays, it's really easy to extend or shorten a linked list. If I want to add an item to this current linked list, all I have to do is just change this pointer and have it point towards another node. Bam, done. If I want to shorten it, all I have to do is change it so that the 2 pointer now points at 4. The 3 box will still exist somewhere floating all by itself, but because there's nothing that points to it, it's inaccessible. You can't get it back. It's gone forever now. The con of int lists or linked lists is that it takes a lot more time to find any object. So in an array, remember we talked about how because everything is the same size and they're all in one slot in memory, you can just bam, 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 you're already there. Well, with a linked list, because they're so modular, each one of these nodes can be stored in a completely different area in your memory, and it would still work fine. So your computer has to, if you want to get the second node, you would have to manually go, okay, this is the 0th node, follow the pointer, this is the first node, follow the pointer, this is the second node. So you have to manually iterate using a while loop or a for loop to get to the node you want. Or that happens within this function. So there's some pros, there's some cons, and it'll depend on what you're using it for what you want to use. Okay, great. So we talked all about some content review. Let's move on to the worksheet. Just like last time, I will state the problem. I will give you 3 seconds in which you can pause the screen, try working it out on your own, and then when you come back, we can talk about it together. So the first problem is called pass by what? We have this lovely class called Pokemon, and it has this main function right here. This is interesting. Just something to note that the main function, although it is traditionally at the top of the class, does not have to be at the top or the bottom of the class. It can be anywhere. There's no specific. It's not like Python in which things are executed in the exact order. Functions can happen in any order, and then it's all good in Java. Okay, so the first thing I want you to do is draw the box and pointer diagram as Java evaluates this main method, and answer the question, what does Java print? I'll give you a couple seconds to think about it. Okay, welcome back. Let's work this out together. So let's draw our box and pointer diagram like we were doing before. So the first thing we do in our main function, we'll write main here so we know what we're in, is we create a variable, p, which contains this Pokemon object. Now remember, since Pokemon is an object, it is not stored within this box, it is stored somewhere else, and we will just have a pointer to it. So I will create my Pokemon instance over here. Its name is Pikachu. Its level is 17. We'll draw a box around it so we know it's one thing. And then we assign this to our variable. So we'll draw a pointer. Great. Okay, first thing's out of the way. Let's get to our next line. So now we're creating a primitive type. We're creating an integer. And this box holds just 100. Okay, pretty straightforward. We've done all the setup. Now let's get into the more interesting part. So like we did before on the pass by value slide, we're going to pass in an integer and an object into a function. This function is called change. Okay, so let's see. We have two variables that get passed in, Poke and level. So for Poke, we pass in the Pokemon that we had made before. And like we talked about previously, that means that this memory address gets copied from P over into Poke. So what ends up in practice is that we have the address of that Pokemon instance. For primitive type, when we pass in level, all we do is we copy this over. And since it's just a primitive type, there's no pointers involved, it's just copied over. And the two levels no longer have any connection to each other. So that's done. Now let's see what this line does. Poke.level equals level. So what we're going to do is we go to Poke and we're like, okay, first of all, what is Poke pointing at? So we go inside the Poke object, which is this Pokemon right here. And then we set the level variable within that object to be equal to 100. This happens because this Poke.level tells us, okay, go to Poke, the object that Poke is pointing at, and find the variable named level. Next thing we're going to do is just set level to 50. All this does is set this variable to 50. And like we talked about before, this doesn't change anything up here because level is self-contained within change. Now this third line is a little interesting. We haven't seen this before. First thing we do, always evaluate the right side. So we're going to create a new Pokemon object. I've been told that this is spelled wrong. I forgot to change it, and I deeply apologize to people who care about Pokemon. I also cannot pronounce it. Gengar, I have no idea. Okay. So we set this, and this is our new Pokemon object. And now we're not changing anything about what Pokemon, we're not changing this Pokemon. What we're doing is we're saying, okay, in the box that the Pokemon that is attached to this variable, we are changing the value of this box to be the value that this returns, which is the memory address that it's at. So what this does in practice is it changes the arrow that it changes what Poke points at to the new Pokemon. This has no impact on the previous thing that Poke was pointing at. This is a little confusing, so if you're not sure what just happened, please ask on Ed, please come to office hours. This is important. We're going to build all this in the future. So now that this is done, we can exit out of the change class and go here. Now we do system.out.print, and now we can get our answer. This prints name, and then we go to p.name, which we can figure out here. Pikachu. Level, same thing, 100. Okay, great. So, just a hypothetical question to wrap up this problem. When we set this level to 50, why doesn't the level up here change? How does the computer know to only bother with the level down here? I'll give you a couple seconds to think about it. Okay, so the reason the computer knows which level to change is, well, first of all, this function is static and this variable is not static. If you don't know what I'm talking about, please reference a previous discussion. But that means that a static method cannot alter a non-static variable anyway. So that's just out of the way. But let's say in the case that this was not static. Let's say in the case that this was also an instance method. Well, the way Java works is the first thing it does when you call on a variable or you give it a variable name is it focuses on the current scope, which is the most narrow possible vision, which is just the current function. Is there a level here? Yes? Okay, great. We're just going to use this level. If there isn't a level here, and in the case that this function was not static, then we would expand our scope to look at the variables that are contained by the entire class. And in that case, we would be able to change this level. Keep in mind, however, we would never be able to access the level that we defined in the main class. That's just out of our grasp, essentially, because it's a completely different function, even though main called change. Okay, let's go to question number 2. So this is called static methods and variables. We have this lovely cat class. On my screen, you don't see the actual question, but basically, the first thing we want to do is there is this main function, public static void main, provided in part A. And the question is, what gets printed after each call of play? I'll give you a couple seconds to think about it, and then we'll go over it together. Okay, let's talk about it. So we have cat A, which has a name, cream, and a noise, meow. Now, one thing that we have to notice when we look at this class is that name is an instance variable, which means that every instance of the class has its own name. Great. However, noise is a static variable, which means all instances share the same noise variable. So basically, all cats have access to the same noise, and so if cat A changes it, then it changes for all the cats at once. And this is important because this will come up when you're drawing box and pointer diagrams in the future. So a good way I like to remember my static variables versus my instance variables is I like to create a separate section that just has the static variables for each class. So here I would put noise equals meow. And this is because there's two things to keep in mind. First of all the instances have the same noise. So this will avoid the accidental issue of you changing noise for one cat and forgetting to change it for other cats, which will cause you to get the wrong answer. Second of all, it just makes it easier to change things in general, to have the static variables here and the instance variables attached to the specific instance. This also reminds you that you don't have to call a.noise. You can also just call cat.noise, and both will work equally the same. Okay, so we have our first item. Let's create a second cat now. So B equals cat dot cat, and its name equals Tubbs. Okay, and now one thing to notice is that Tubbs has a noise Nyan. And so when we set the noise to Nyan in the constructor, it's a static variable, so we're changing the noise for all the cats, and we're going to do that over here. So we've done the simple part, we've done the first construction. Now, what does A.play and B.play print the first time? Well, I won't write out everything, but it prints the noise and the name. So the first time it prints Nyan cream and Nyan Tubbs. Does this make sense to everyone? If not, please ask for help. Okay, so we've done that, and now what we're going to do is we're going to call cat.anger. And what does cat.anger do? Well, it calls this static function, and it's static, which means we're allowed to call it on just cat. And what it does, it sets the noise to uppercase. So we're going to do that. Great. And then the next line says, okay, we're going to do a.com, which com is also a static method. So we can't call it on cat, but we're also allowed to call it on instances. Every instance has access to the same static variables. So even if you call it on an instance, it can still go into this little section and edit stuff. So what it does is it says it's a lowercase, so we can go like that. And now we have our second round of A.play and B.play. So the first line prints Nyan cream, because we go to the noise, that's the noise. We go to the name, that's the name. The second line prints Nyan Tubbs. Okay, we're almost done. Just one more action. So now what we're going to do is we're going to call a.nickname. And what this covers is nickname is an instance method, which means it can only be called on the instance A. And if you think about it just conceptually, you can't, each cat has a different name, right? So if you were going to just nickname cat, which cat's nickname would you be changing? Which cat's name would you be changing? It doesn't make any sense, which is why you have to call nickname on a specific cat, on a specific instance of a cat. So now that we've done that, we'll change the name of A to its new name, which I forgot to write here, but is actually Kitty. So we'll change it up in our little box and pointer diagram. Just like that. And so we go here, and in our third round of A.play, B.play, we print the same noise as before. Kitty and Nyan. I'm Tubbs. And Tubbs does not change because the name of cat B is completely separate from the name of cat A. Okay, now a hypothetical question. If we were going to run cat.nickname, Kit Kat, what would happen? What would our computer do? Well, in this, if we were supposed to add this to our main function, it would error. Because in this class, nickname is an instance function, so like I said before, it doesn't really make sense to try to nickname cat as a class of objects. You have to nickname a specific cat. In general, there's only two main things that you have to remember. One is that instance methods can only be called on instances. And two is that static methods can be called by either instances or just the class itself, but can only change static variables. These are called like the golden rules for static methods, and if you want more information, go watch lecture. Okay, let's get to the last non-extra problem. This one's a little tricky. It's just practice with linked lists. This problem is something that is a little more complicated, but with practice will become more straightforward. So, let's follow this line by line like we always do. I'll give you a couple minutes to think about it. Okay, let's get started. So our first line says we create a variable called L, and we point it towards a new string list called eat. So let's create a string list object. We can symbolize that with a box with eat, and then this points nowhere. So L points at that. Next, we get another string list object called shouldn't. And we always evaluate the right-hand side before the left-hand side. So we set the rest or the pointer at the end to be equal to whatever L is currently pointing at. We basically, again, copy over this memory address from there over to here. And so what that means is shouldn't points at eat. And now the last thing we do is we assign this new string list to L, which gives us something like this. Now let's do this basically 2 more times. I won't talk through it as detailed, but it's basically these 2 lines. We create one that says U, point it at shouldn't, we adjust L, and then we create the last one, which is sometimes. And that points at U. And then I'll move this up a little bit so it's a little easier to see, but this points at shouldn't. Okay, great. We created our first string list. Now we're going to create a new variable called M, and this one is going to point at L.rest. So L.rest is, so we go to L points at this object, so this is, we'll go here. And then we're going to copy over the address from L.rest into M. And what that translates to is that M will point at the same thing L.rest is pointing at, which is U. Great, that's done. Now, we're going to create another string list called R, and we're going to create a string very similar to the way we did before. Many, null, and we set R equal to that. And then we create another string list object, potatoes, and we set potatoes to point, the potatoes.rest to point at many, and then we just move this R pointer down again. Okay, here's where things get a little more tricky. There's lots of rests involved, but all you have to do is think through it. So the first thing we do is r.rest equals r. And what does that mean? So we start at r, potatoes, and then so this we can consider to be r, and r.rest is this object. This is the object within r.rest. And this is the specific variable that we're changing. We're changing the value of r.rest. And so we're changing it to be equal to r. So we're copying over the memory address from r over into there. So, like we've done so many times today already, what this means is that this now points at the same thing that r points at. This is weird now cyclic linked list. Okay, great. We've done that. Let's do m.rest equals r.rest. So we do the same thing. M points to here, this object. M.rest points to this object. M.rest points to this object. And so the actual variable that we're changing now is this variable, is m.rest. And we're going to set it equal to r.rest. So we go to r, we have this, and this is the memory address that we're copying over into m.rest. So what does it point at? It points at the box with many in it. So we're going to draw an arrow from eat to many. Okay, so we've done that. Now we have to do l.rest equals l.rest. Again, we follow just the same exact overall strategy. We start with L. This is the object that L points at. L.rest points at this object. L.rest points at this object. And L.rest points at this object. And so if you remember, this is the pointer we're changing because L.rest, and then this is the .rest pointer within L.rest. And we're going to copy over the value from this pointer into there. So essentially, we're just redrawing this arrow to look like this. And now the last thing we do is we set L equal to m.rest. And so what that means is we have m, hold on, let me get rid of these little marks in the corner again. Okay, so we have m right here, and then m.rest points to this object. And so we're setting L just equal to that. So we're just going to point here. And that is the final form of our very complicated linked list problem. Don't worry if you didn't get on the first go. Just try it again and go slowly through all of the different linked lists. Great. Okay, let's move on to problem 4. This is an extra problem. It's gonna be rough. I'll just let you know now. So, the first thing we're doing is we are trying to square every item in this int list non-destructively and recursively. Non-destructively means the int list L that you're putting in will not get changed at all. The int list that you return should be a different int list. and you shouldn't mess with int list L at all in the process. Okay, I'll give you a couple seconds to think about it. Okay, let's work on this together. So, the first thing we know is that this is going to be recursive. And whenever something is recursive, there's two things that we have to always look out for. What is the base case? And what is the recursive call? Okay, so let's do the base case first. So when do we want this to just end? When do we not want to keep going? Well, theoretically, when we're on the last item of the list, right? Because when you're on the last item, then there's nowhere further to go. Great, okay. We can write if L.rest equals null, because if L.rest equals null, then we're on the last item. One thing to note, though, is this is a thing called arm's length recursion. The best thing to do is, instead of doing L.rest equals null, you should be checking to see if the list is already over. And you can do that by saying if L equals null. Because if you think about it, at some point we're going to call it square list on L.rest, right? To get the rest of, to square the rest of our list. So eventually, we will call square list on the rest of the very last item, and it's a lot easier to handle this case where we just return L than having a separate case where if L.rest equals null, then we have to do the same thing on L that we have to do on everything else. We just have to not make that recursive call. So the idea is to keep our base cases as simple as possible. And the way to do that is to only end it when you're actually at the null and not when you're just expecting the null. Okay, we will talk more about that a lot later in this class. So now we have our base case, that's check. Let's figure out what our actual recursive case is going to be. So let's see. First of all, what are we doing to the current node of this int list? Well, the first thing we're doing is, well, of course, we don't want to actually edit anything in this int list. So we want to create a new int list, right? Int list. Let's call this M, and that equals new int list. And then we're just going to square the first item. L.first. Great. Okay. But what's the rest going to be? Well, we want the rest to be something to already be squared, right? Where we don't want to create the rest and then go into int list square, because if we do that, then that'll create a whole new list. It won't edit the list that we already have. So what we need to do first is, you'd also use in the same line as here. I just like doing it on a separate line so that it doesn't go off the page. But what you have to do is call square on the rest of our int list. And this way, this will already be squared. And we don't have to even think about that anymore. And we just add that to here. And we return our new int list that is not the same as we had before. This relies on the recursive leap of faith that I talked about last time. This line in particular makes you assume, okay, I know what I'm doing right now is correct. I know that assuming that rest gives you back a squared list, then M will return the correct thing. And because I know that, that means that I can assume that all of the other recursions of this also return the correct thing. Okay, great. Don't worry if it took you a while to figure this out or you didn't figure it out. This is an extra problem. It's meant to be more difficult. It's always hard to figure out how to write code for things like this. Okay, part B of our squaring a list is this time we want to do it destructively and iteratively. So destructively means this list is the one that we're going to edit, and iteratively means instead of calling on square destructive over and over again, we are just going to use either a for loop or a while loop. I'll give you a couple seconds to think about it. Okay, let's reconvene and think about this. So let's talk about this visually for a second. So I have this int list, let's say it's 1, and then it's 2, and then it's 3, and whatever. Let's say it's 4 items. Okay, great. So what do I want square destructive to do? I want it to basically go inside each of these lists and then square the items. I want this to become 4. Well, this is already 1. And then this to become 9, like insert itself and change it, and then we'll return the same list. So how do we do that? How do we individually get to each item in the list? Well, let's see. Visually, something that we could do is we can first, let me get rid of all these extra arrows. The first thing we can do is we can start on the first item in the list. Okay, first thing first, we double this. Great, it's doubled. Now we can follow this arrow from L.rest to get to the next item and then do the same thing. And we just keep going down this list, doubling and then moving to the next item until we hit null. Now, can we just do L equals L.rest over and over again? Technically, yeah. But the problem with that is, in the end, we want to return the same int list we passed in. And so, remember, this is not doubly linked. Once you go this way, you can't come back. There's no pointer taking you from item 3 to item 2. There's only a pointer taking you from item 2 to item 3. So we need some variable that keeps its eye on the first item, and then another variable, which is the one that moves down slowly over time. And that way, the second variable can do all the different manipulation, and the first variable can remain present so that in the end, we can return the original list. So how would that look like in code? The first thing you want, like I said, is the other pointer. So let's just say int list b, just a random variable, equals L, because we want to start off on this node. And when do we want to stop? How long? What is the condition for when we want to not go anywhere anymore? Well, when b would equal null, then there is nothing to double, right? There's no null.first. That doesn't exist. You'd cause a null pointer exception. So we can just keep going until we hit that case. We can just say while b isn't equal to null, then we do something. Well, one thing we know we have to do at some point is we have to go from b to b.rest. And now, the only things that we have left are, of course, we also return our L. And now I have to figure out what goes in this space. What do we actually do? What does b do when it's on each element? And the answer is it does b.first equals b.first times b.first. There's more elegant ways to write that line, but this is just a most straightforward way. Once we hit null, then there is no b.first, there is no b.rest, so we just exit this while loop and we return L. Okay, 2 more parts to go. We're doing the full cross section. So we did it previously, non-destructively and recursively. Now we want to do it non-destructively and iteratively. Now this is actually a little bit harder. So I'll give you a couple seconds to think about it. Okay, welcome back. Let's talk about it. So we're doing this iteratively. Okay, so let's get started. So let's see, we're going to want to adapt our destructive iterative method into our non-destructive iterative method. So let's again do this a little visually. We'll start with 1, 2, 3, 4. Great. Okay. So remember, we don't want to mess with this original. This should look exactly the same when it comes out, and it should be the same squares too. So instead, let's create a version of L that's like squared L. And let's figure out how we're going to do this. So squared L is going to be equal to, we're going to create a new int list node every time, and we're going to copy this item here, except we're going to square it in the process. So we'll create this node, and then we'll create this node, and then we'll create this node, and then so on like that. Most important thing is we're not editing the first list, we're just moving through it and taking its value and putting it in the new list. Okay, so the way we are going to approach this is first, let's create our square list. So our new int list square list is going to be equal to a new node, because we don't want to mess with the old nodes on accident, that has the same value as L.first, but squared. And for now, we can set the rest to be equal to null, because we haven't calculated that yet. So, one thing to remember is that you need access to L dot. So first of all, remember, we need this pointer to remain where it is, because if it moves, then we have no way of returning the square list. So we're going to need a different pointer like we did last time that actually moves down the list. So we can use the same notation we used last time, and do int list b equals square list. So what we're also going to want to do before we get into the while loop is just iterate L once, because we don't actually have to keep this. We're not returning this one. So it doesn't matter if this pointer moves down the list, because we don't need it in the future. So what we're going to do is you're going to set L equal to L.rest. Now we can follow kind of the same structure we did before. Once L reaches a null, that's when we know that we have hit the end of our list. So we can always just set while L does not equal null. We do the thing, and then once that's over, we return our square list. Okay, here comes the tricky part where we figure out what we have to do on the inside. The first thing we do is we have to set b.rest Because right now b.rest is null. So we want to create an int list and plop it in there, right? So we want to set b.rest to be equal to a new int list. That has, again, we've iterated L, so now L doesn't point here anymore, it points here. So we can do the same thing that we did above, L.first times L.first and null. And then we have to set b equal to b.rest. So we're basically moving our frame from looking at this to now we're looking at this. And we're just repeating the same process over and over again. And then the last thing we do is we also have to iterate L. So that now we're going to be, now that we're looking at, let's say, this block of squared L, we also want to make sure that we're going to be copying in the value from the corresponding block of L. So this is it. This is our final form. Don't worry, this is a very tricky problem. It's just for practice if you want to prepare for tests and such. Okay, the very last problem. We're going to do the same thing one more time. And this time it's going to be destructive and recursive. So, think this through. It's easier than the last one. And we'll talk about it in a couple seconds. Okay, welcome back. So again, with the recursive thing, we're going to do two things. Base case, recursive call. Okay, let's go. So the first thing we do is figure out our base case. And it's the same as last time because of the same reasons. Once L is equal to null, there's nothing more that we can do. All we can do is return null, or it doesn't even matter because we know what L is, we can just return L. Okay, great. That is out of the way from the beginning. Now, we know that ultimately we want to return L because we're doing this destructively. So that's the third line. But there has to be some recursive call, and we have to do something to our current list. So much like last time, what we want to do is, since it's destructive, we don't even have to set things to each other. We can just call square destructive on L.rest, and it will automatically cause L.rest to be squared. We don't have to manipulate anything in this function to do that. And then the last bit of it is we need L.first to be equal to L.first squared. And so what this does is essentially, when you're on a block, let's make this 2 so it's actually, when it squares, it's actually noticeable. But you square this, and then you call square destructive on the next node. And so it goes in there, it squares it, it returns L, but you're not setting that equal to anything because you don't have to. And then you just return this. Okay, well, that was discussion 2 for CS61B, and it was a little bit of a long one. So, if you have any questions, again, ask on Ed, ask in office hours. We are always happy to answer conceptual questions about discussion. Good luck with your second week of school.